And first speaker is Ismael from NCC. He's going to speak about numerical analysis of traveling waves in Porous.
Thank you, Pablo. Good morning. Today I'll present to you some of my work with Dan for the past 1.5 years. And this is a joint work with Professor Plot too. And this is some of the things I'll talk to you today: traveling waves, then saddle-to-saddle connections, saddle-to-saddle node connection, and then we'll solve human problem using these type of connections. So in my the model I'll be using here is the Coracoid Module. Basically, you have saturation of water, saturation of gas, and these are very commonly known formulas. More details about this model is in this article published in 2001. Here we have the flux function, the accumulation, and this is the viscosity matrix. We can put it in a Oh, sorry. Okay. Can everyone hear me now? Okay. Sorry. So we can put this model in this general form here, in which we want to make epsilon tend to 0. And as I told you, now here the saturation of water and gas are represented by the variable u, which is a vector. G is the accumulation function, that's the general accumulation function. F is the flux, and B is the diffusion matrix. So we're interested in studying traveling wave solutions. Basically, in order to find those traveling wave solutions, we make a change of variables, and then we can write the solution in terms of a single variable, and then we transform the original PDE into an ODE. Using this condition, we can get to this final formula. And we are now interested in solving this system of ODEs. Here we have a fixed left state, UL, and FL is the flux function evaluated at the left state, and GL is the accumulation function evaluated at the left state too. So we have the Hugoniot locus, which is the set of right states for which this expression is valid. Oh, sorry, I forgot to mention that we have the sigma here, which is the velocity of the traveling wave. In this case, the sigma is the shock speed for the Hugoniot locus. And our problem now is to identify what points of the Hugoniot locus we can make a connection from the left state to that point. Here you notice that because of this formula, then the left state and the right state are equilibriums of this system of ODs. So now our problem is to study the field given by this system of ODs. We have the shock speed, we have the left state, and we want to study the field of this system. So we make a linearization about some equilibrium W star, and we see that now we just have to study the eigenvalues of this matrix here for the when B is the identity, so its inverse is the identity 2, and then the eigenvalues are actually the characteristic speed minus the shock speed. And those are very known admissibility conditions for slow shocks and fast shocks.
I guess there's a printing error in the first one, is that right?
The first?
Lambda 2UL is bigger than lambda 2UL line. Yeah.
Okay.
You mean something else, I don't know.
Yes. Anyways, it's a repeller to a saddle connection. Yes, the index is 3, right? Yeah, it should be 1 here, and should be 1 here. Okay, so here's a picture of a slow shock connection. We have a connection from this left state to this right state, and we see that many orbits leave the left state, but only one enters the right state. Here's a little video. Oh. Just to show that a lot of points have connection. A lot of points along the Hugoniot locus. This is the Hugoniot locus, and in blue here is the slow family. By looking at the video, we see that a lot of points of the Hugoniot locus provide a repeller to saddle connection for the slow family. This is the fast shock. Now the saddle is at the left state, and we have many orbits entering the right state, but only a few leaving the left state. And as previously, there are also along the Hugoniot many points for which we can find saddle to attractor connections. However, we are interested on saddle to saddle connections because only a few orbits enter and leave the right state as well as the left state. So those are a little bit more difficult to find. And when we search along the Hugoniot, here we have the transitional region. Those are the points for which you can define a saddle here and a saddle here. And when we look at this picture, we see that when we draw the invariant manifolds leaving and entering the equilibriums, basically only one equilibrium here provides a saddle to saddle connection. And we want to find this equilibrium precisely. So how do we do that? We see that the orbits get close when we move along the Hugoniot. We want to know for what point they coincide here. This is the one we're looking for. Okay. So the solution is that we draw a line here. We call this the Sotomayor line. And then we define 2 points on the transitional region such that when you draw the invariant manifolds and you follow, you attempt to make a connection from the left state to the right state, the orbits cross this line. So if you define this D plus vector to be the crossing point here, from here to here, you'll see that for one point, this vector points to the right, and for another saddle, this vector points to the left. This is the situation we are interested in. All right. So I'm going to present to you how is the algorithm to find precisely what's the point such that we start an orbit here and it ends up in a point here. Okay, so first we already have 2 points that provide difference vectors pointing one to the right and one to the left. So we pick the point in the middle. When we do that, now we notice and we draw again the invariant manifolds. We get another difference vector, and now this vector points to the left. So because it points to the left, we eliminate the last UR, whose direction vector pointed to the left, and we have now a smaller set of points to deal with. And we go on one more time. Now we eliminate the previous point, that the UR plus, and now we have an even smaller region to worry about, and we go on. At this point, for us, as long as we can see, this is the saddle-to-saddle connection. So there's a tolerance. You are looking for, you are making a binary search to find the saddle-to-saddle connection. Here's a simple algorithm to find this connection. Basically, in order to know if you want to choose the middle point to be the left or the right, you make the internal product of the difference vectors. If it is positive, then they point to the same direction. If it is negative, they point to opposite directions. Okay, so now once you have found saddle-to-saddle connections, if you have a region where you can always find more saddle-to-saddle connections. However, if you move too much to the right or too much to the left, you lose the saddle-to-saddle connection. In order to solve human problems, we want to find also this boundary here, the transitional boundary. So now our problem is, how do we find precisely for what points, what are the left state and the right states for which we have, in this case, saddle-to-saddle node connections, because you see that this point tends to this little square right here, which is a right state for which the shock speed matches one of the characteristic speeds. Okay? So one possible algorithm.
Could it ever happen that it instead hits another equilibrium in the middle? Did this ever happen? Because that could also break your connection.
Well,
It didn't happen.
It didn't happen with me. I can't tell if it could happen, but yes, you're right. I didn't think about it.
Depends on the complexity of the system.
Yes.
You have things between when it appears, no? It may appear.
Yes.
On the systems itself.
Mm-hmm.
All kind of complexities you can produce artificially or depending on the program.
Yes.
Well, first it's true. I check whether the other space. Once the terrain is clean, then you go ahead and use this bazooka.
Yeah, it didn't happen to me, so I can't tell if the algorithm will fail. But because we're looking for saddle-to-saddle connection, if at some point there is no saddle-to-saddle connection, then I'll attempt to make the boundary anyways. So we want to find the boundary, and one very simple algorithm is you have a point for which you have a saddle-to-saddle connection, and you have another point for which you don't have a saddle-to-saddle connection. You make a segment connecting those 2 points, and now you do a binary search to make you do a binary search to find the limit, to find the boundary point to be limit of saddle-to-saddle points. So for example, here you have a connection. Here you don't. So you take the middle point and check whether you have a connection or not. And then you eliminate one of the left or right. Now you take another middle point and so on. However, this is very expensive because every time you want to check if a point has a saddle-to-saddle connection, you have to go all over the transitional. 5 minutes? Okay. So this is a very expensive algorithm, and we want a better one. So this is a video showing the next one. We draw invariant manifolds leaving the tick mark now. And at some point, when you move the left state, you see that those invariant manifolds will cross. So the idea is basically very similar to the other one. Now we draw invariant manifolds leaving one of these tick marks for which the shock speed matches the characteristic speed, and you define another difference vectors, and you do another binary search. Now the algorithm is much less expensive because you do one invariant manifold for each equilibrium. You don't do many along the whole transitional region. Okay, so this is basically how the algorithm works. You start with 2 points, 2 left states, okay, and you draw the invariant manifolds leaving the left state and entering the tick mark here, which is the right state, and then you select one left state in the middle here, and using that new left state, you eliminate one of the previous ones. And now you have another smaller region to look for, and you go on and on. And at this point, you already have something that look to the eye like a saddle-to-saddle node connection. Okay. So this is an algorithm, as before, to decide what side you want to decide what left state you want to discard at some iteration. You check the internal product of the difference vectors. Okay. So this is just a plot of how the saddle-to-saddle node connections will look like when you check them at the transitional boundary. Finally, we are interested in solving Riemann problems. So this is a wave curve for the left state. Basically, as Dan explained in his talk, we join pieces of rarefactions and shocks, and we want to connect the left state to the right state. Now, we have to check some admissibility conditions, but basically you check here that the wave curve for the left state crosses the transitional region, and the wave curve for the right state crosses the corresponding transitional region. So there could possibly be a transitional connection between one point of this wave curve to this wave curve. So we want to check that. We want to check if there really is a transitional connection. Okay, so I'm going to tell you how I choose the left state and right state. But again, we want to move along one wave curve and check whether those two invariant manifolds get very close to each other. So how do we define the left state and the right state now? Okay, so we find the intersection of the fast backward wave curve with the transitional region. We will have a little segment here. Then we draw a Hugoniot for one of these points. Okay, we're not interested on some of the points. We just leave the transitional ones. Now, one of the transitional ones will possibly cross the slow forward wave curve. If it does, we choose the left state. The left state should be the intersection point. Then we draw the invariant manifolds as before. So basically, we go along the wave curve. We draw Hugoniot locus. We find the intersection with another wave curve, and we draw the invariant manifolds. If at some point we see that the difference vectors changing in direction, we can apply a binary search again to find the saddle to saddle connection we are interested in. In this case, there really is one connecting this point to this point. If we want to verify if this is really a saddle to saddle connection, we just plot the field and we check that it really is a saddle, it really is a saddle too. And if we want to verify the Riemann problem, we make a simulation, and then we verify that we have a rarefaction here corresponding to this part. Then we have a shock right here corresponding to this transitional connection. And then a rarefaction and a shock corresponding to these two connections here. We can also plot these points, and we check that they go through the same path we had before. Okay, this is all. Thank you.
Any questions or comments?
No. Okay, so this is just a very small piece of it's unimportant, but to find whether you're inside or outside the transitional region, what do? Do you use a winding number or an intersection?
To define if I'm inside or outside?
Yeah, because you have you know the boundary. You found the boundary as a vector of a series of vectors, correct?
Yes.
And now you need to check. What's the computer algorithm you use? Like you take a point and you ask if you're inside or outside. It's probably the same.
You mean when I go along this curve, I want to know if I'm inside the way?
Inside that curve, yeah.
Okay.
You have a point on your Hugoniot.
Mm-hmm.
How do you check if you're inside or out?
Well, for the moment, we simply look and we know.
Oh, okay.
So in the future, yes, we'll have to implement something to determine whether this point is inside or outside. I'm sure there are many algorithms, but for the moment, we look here and we know that this little piece is inside. Any other questions?
Well, he has a method
Well,
to talk about.
Yeah, but there's probably, like you said, like Microsoft Draw or something has a method.
Yeah.
I'm sure there are standard methods.
Well, the truth is that the transitional region, this is numerics, right? So this is quite not connected. So numerically, those pieces are not connected numerically. So there are a few problems, but yeah, we still have to worry about it.
So I was, this Damascus and also Diamonds having a problem like that because we were trying to simulate steam displacement.
Uh-huh.
And the nice thing about it was that actually, I have been walking around 10 years about that. I thought I'm missing an equation. And the extra equation was, of course, exactly where you get this saddle-to-saddle connection. So it gives you an additional equation in your macroscopic system. That is really nice, is it right? Because you like...
You mean to identify what are the saddle? What is the transitional region?
Yeah, well, you had, we wanted to know what is this, steam. We wanted to know what is the residual oil saturation. And we didn't have an equation, and then for the saddle-to-saddle connection, if that was working, you got exactly the point. So you are actually able, with the saddle-to-saddle connection, to get additional information. Is that right?
Yes. But are you asking how I find the...
No?
No?
Just mention
Yeah,
this
okay.
as a possibility, and is that also your feeling that is?
Okay.
No?